black holes tearing apart enormous stars, pulsars spinning at incredible speeds and emitting powerful beams of energy, colorful nebulae with fireworks of newborn stars, galaxies of every possible color and size. All of these are found within our universe, but it's not infinite. It has a boundary, a literal wall, and beyond that, there's an absolute nothingness. Right now, we're going to make a journey to that wall. But first things first, our universe is like a humongous nesting doll. If you open it up, there's a smaller one inside. It's a galaxy. Inside that is an even smaller doll. That's our solar system. And the smallest doll of all is the Earth. Each of these dolls has boundaries that we're going to cross. For that, we'll need a spaceship, and a big one. It also has to be able to move 100 times faster than the speed of light. You get on board and start the engines. 62 miles above sea level is our first boundary. That's 10 times higher than passenger planes fly. This point is called the Kármán line. It separates the atmosphere of the Earth from outer space. Now we fly further to the edge of our solar system. We turn on the hyperdrives and fly past Mars, Jupiter, Saturn, Uranus, and Neptune. We've traveled a distance of 100 astronomical units. 1 AU is the distance from Earth to the Sun. And here's the boundary of our solar system, the heliosphere. Here, the speed of the solar wind decreases rapidly. First, it drops from 620,000 miles per hour to the speed of sound. Then, there's a layer called the heliopause. This is where the wind almost vanishes. And then, our ship experiences a bow wave. This is where we feel the force of the interstellar wind, which collides with the boundary of our solar system. When you pass this boundary, you find yourself in the dark of interstellar space. And here, you can find 2 human-made objects that made this trip for the first time in history. They're Voyager 1 and Voyager 2. Voyager 1 crossed that boundary in 2004. Voyager 2 did it in 2007. These space probes discovered that the heliosphere is not a perfect ball around the sun. Its southern boundary is 10 AUs closer to the star than the northern one. So, we're moving in interstellar space and will soon approach a stone wall around our solar system. 200,000 AUs further, and there it is. This wall of rock is the Oort cloud. In fact, it's a pile of asteroids that surround our world. Scientists speculate that the Oort cloud could be the source of comets and meteorites that fall to Earth, but they're so sparse that we easily fly between them. Now we're in complete darkness. The Milky Way is about 106,000 light-years wide. In a conventional rocket, it would take billions of years to fly across that distance. But you throttle to the max. You masterfully fly past the stars and planets as if on a racetrack. And within minutes, you're at the edge of our galaxy. There's no more interstellar wind. All you see are bright dots somewhere in the distance. These dots are huge galaxies. We need to look at a map to make a route to the edge of our entire universe. You're here, near the Milky Way galaxy. It's part of a cluster of galaxies called the Laniakea supercluster. But even this huge thing is like a little street in a big city. Zooming out, we find Hydra Centaurus supercluster. Thousands of galaxies on the map look like little dots. Maximum zoom out. This is our entire observable universe. We thought it was infinite, but we may have proof that it has a boundary. It's here, 10 billion light-years away from our home. Even if you travel at the speed of light, a trip there would take twice as long as our whole planet has existed. During that time, the sun will either fade away or explode like a supernova, destroying our entire solar system. And if you can live that long and then return home, you will see that our galaxy is there no more. It's long since collided with the Andromeda galaxy and merged into one big cosmic body. Luckily, your ship is able to warp space-time so that this journey will literally take a few seconds. Boom! Congratulations! You've arrived at your destination, the Eridanus supervoid. Some scientists believe this location is the evidence of collisions of our universe with something big enough to leave such a large scar. The Eridanus supervoid is an empty and cold space 1 billion light-years wide. If you think of this void as a cup, it would fit at least 10,000 galaxies, and it appeared after an accident of gigantic proportions. The object that crashed into our universe was Another universe! Yes, other universes may actually exist. Imagine that our entire universe is a huge bubble that contains all the clusters of galaxies in the observable universe. There could be an infinite number of such bubbles. They could have been born during the Big Bang. These universes may be different from ours. They may have other galaxies and nebulae. But these bubbles could also be parallel universes. This means that if you chose cereal over oatmeal in the morning, in another universe, your twin would choose the oatmeal. Every choice you ever made in life had completely different consequences in a parallel universe. And because the number of choices are infinite, there's a whole infinity of parallel universes. So, like a regular bubble, our universe has a wall that is near the Eridanus supervoid. Long ago, another bubble flew past ours. As they approached each other, their gravitational fields began to interact. Our boundary wall began to deform and pull toward the other universe. The same thing happened on the other side. Then the walls of our universes came into contact. But as these bubbles moved, their connection began to break, and the other universe just ripped a huge chunk of ours. A cold void was formed at the point of collision, and that was the Eridanus supervoid. The problem is that the universe looks the same to the observer, regardless of point of view. For example, imagine a basketball hanging in the air. Now, if we put an ant on the ball and tell it to find the edge of the ball, it will start running around it, making an infinite number of circles. But the landscape around the ant will not change. All it will see is a rounded horizon. That's because the ball remains the same from any point of view. The same thing happens to us when we try to find the edge of our universe, all because we imagine the world in three-dimensional space, and our view is limited. For example, you see an ordinary square in two-dimensional space, but if you add depth and change the point of view, voila, it's a cube. If we could see the universe in four-dimensional space, a square might be something completely different. But maybe we can leave our home bubble. The key to traveling to another universe might be inside a black hole. A black hole is one of the most mysterious objects in the universe. They're so heavy, they warp not only space, but time as well. It's like putting a heavy boulder on a net. The net will sag, and the closer you get to the boulder, the stronger the curvature is. Once you're in the gravitational field of a black hole, you can't leave it. We still don't know what might actually be in the heart of a black hole. Some scientists speculate that white holes also exist. Theoretically, they should be born along with black holes. Except for the color, they're the exact opposite of black holes. Nothing can come close to a white hole. At the moment, there's no data on such objects, but general relativity theory suggests they do exist. There's also a theory that a black hole may be a passage to another universe. When you get into a black hole, you can come out the other side through the event horizon of the white hole. So you bypass the boundary of the universes and find yourself in a completely different world. But we may have proof that a white hole exists. In 2006, scientists discovered an unusual burst of energy somewhere 1.6 billion light-years away from Earth. This burst was unique. It didn't look like a supernova explosion or even the merger of two black holes. Some astronomers believe it was the birth of a white hole. But because it was unstable, it was destroyed almost immediately. This process was reminiscent of the birth of our entire universe, the Big Bang. So, scientists called it the Little Bang.
This is our home planet Earth and its satellite, the Moon. Zooming out, and here's our solar system. A bit more, the Milky Way galaxy. And we're a small dot among an infinite number of stars. Now, even farther out, a cluster of galaxies. Dots and swirls in the endless space. Further, there's Laniakea supercluster. That little dot here is our galaxy. Moving on, Hydra Centaurus supercluster. Huge clusters comprising thousands of galaxies are no more than a speck from here. Next, Pavo Indus supercluster. This is an area 200 million light-years wide. We can zoom out until we see the entire observable universe. Each little dot in here actually contains thousands of galaxies and quadrillion stars. Scientists speculate that our universe may look like a bubble, and that bubble might collide with another universe. Yes, other universes could exist. Actually, even a whole infinite number of those. All of them could have appeared after the Big Bang. The collision between them isn't impossible either. At least, it might have happened before. And the proof is here, in the direction of the constellation Uranus. This place is called Uranus Supervoid. It's about 1 billion light-years wide. By comparison, the width of our entire galaxy is only about 100,000 light-years. There's absolutely nothing in this place, and it may be a trace from an old collision between our universe and another. Scientists think they were passing by each other. When the distance between them was minimal, the gravitational forces of the bubbles began to pull toward each other, just like two drops of water trying to connect when they're close. But the speed of the universes was too high for them to continue interacting, so the other universe just tore out a piece of our bubble. There might have been about 10,000 galaxies in that void, and all of them were either destroyed or taken over by the other universe. Let's travel to the edge of our universe to see how this collision might have taken place. We're 10 billion light-years away from our home. Here, in another galaxy, we see amazing nebulae of different colors and shapes. And if you look in the other direction, there's a huge wall moving at us. All these bright sparks on it are enormous galaxies about to collide with us. But in fact, it's a humongous mirror that only reflects our universe. Here, space-time is distorted and begins to be pulled into another universe at a tremendous speed. The usual law of physics may simply stop working at this point. Gravity may disappear, and with it, all the stars would explode and people on the surface of planets would hang in weightlessness. But if the universes didn't go at a tangent but crashed directly into each other, things would be much scarier. The enormous amount of collision energy would probably cause an incredible explosion. Its force would simply destroy everything in our bubbles. Still, the two bubbles might begin to merge too. At first, all galaxies at the edge of the universes would be torn apart, but then the merger would begin. The galaxies would start moving chaotically. They would fly past each other, break apart, collide, and explode. The collision of two galaxies is an accident of enormous proportions, and it might happen to our home quite soon, in space terms. The Andromeda galaxy is heading our way. It's a spiral galaxy about twice the size of ours, and there are about 1 trillion stars there, which is twice more than in our Milky Way. At the very center of this bright galaxy lurks a dark beast, a black hole. Its weight is 2 and 8 zeros of the Sun's mass. Red giants hundreds of times larger than our Sun. Pulsars emitting enormous amount of energy like spotlights. Rogue stars, and many large and small black holes. This soup of dangerous objects is moving toward us at 68 miles per second. A trip to New York to Los Angeles at that speed would only take half a minute. The disk of Andromeda can already be seen with the unaided eye on moonless nights. As time goes on, it'll get even bigger. As Andromeda gets closer to us, its gravitational force will begin to stretch the arms of our spiral galaxy. It'll begin to unwind. The stars and planets will lose their orbits. One possible scenario is that an unknown asteroid, or even a dwarf planet from the Andromeda galaxy, will crash into the Earth at an incredible speed. Our planet will explode just like a balloon from this impact. Oh, goody. Another option involves stellar collisions. Our Sun would face another star. The bigger star will slowly begin to consume the smaller one. First, it will steal the light upper layers from it, and then it will eat it just like spaghetti. Or even like rigatoni. When a large star reaches its critical weight, it will burst. This explosion will destroy everything around it, including our solar system. Perhaps the shockwave will even reach other neighboring stars. Yet another scenario is that our solar system will be thrown into dark space. Imagine a tennis ball tied to a rope. You take the rope and spin the ball over your head like a sling. Then you let go of the rope and send the ball flying. This is what will happen to the Sun and all the planets around it. We'll find ourselves in dark and cold space. But life on Earth will not be affected. We'll still have our bright star to keep us warm. The only disadvantage is that all the stars in our night sky will disappear. And the most likely possibility is that the merger of two giant galaxies will have no effect on us at all. The thing is, the distance between stars and planets in space is enormous. So they can all just mix together and form one giant cloud. It would be like shoveling fine sand through a big sieve. The objects won't interact with each other. But the most interesting thing will happen to the black holes in the centers of our galaxies. Right now, there's a dense cluster of stardust and stars around them. As Andromeda and the Milky Way come closer together, they will begin to dance with each other. Gee, will it be the twist or the foxtrot? And when the black holes get close together, they'll begin to swallow all matter around one another. Billions of tons of colored stardust, asteroids, and star particles will fly toward the very center of either black hole. It might seem like this process happens very slowly, but it's an illusion. Super heavy objects like black holes warp the space-time grid, so time is much slower near black holes. And all objects that seemingly stay on the event horizon for weeks or even months are actually long gone. When the black holes finally come together, they merge into one supergiant black hole, but its mass is slightly less than the combined mass of the two dark monsters. Some of their weight is transformed into collision energy. This energy is released so strongly that its waves can be felt in other galaxies. Now, a huge black hole gathers all this dense and hot core of the two galaxies around itself. At some point, the black hole feels full and throws out powerful jets of energy into space. This is called an active galactic nucleus. It's one of the brightest phenomena in the universe and the most powerful source of electromagnetic radiation ever known. These jets may be more than 5,000 light-years long. By comparison, the distance from Earth to the nearest star, Proxima Centauri, is only 4.2 light-years. And the explosion that accompanies the jets has the power of 100 supernova explosions. Wow, blows my mind. The blast wave from this event could even reach the edges of a new galaxy, and this outburst would be visible from millions of light-years away. Now, there are dense clouds of multicolored dust at the center of merged galaxies. The weight of these clouds is so great that they begin to shrink and take on a round shape. Gradually, they become so heavy that they compress the core and nuclear reactions start inside them. The temperature begins to rise and soon, boom, there's a supernova. It's a veritable fireworks show at the center of the galaxies. Stars erupt from the fog and form new hot worlds. At this point, the arms of the two galaxies that were previously pulled out slowly return to their former shape. The super-heavy center of our galaxy has such a gravitational force that it affects stars and nebula hundreds of thousands of light-years away. The galaxy's arms twist again, and we see the new and finished galaxy, the Milkomeda, or Milkdromeda. Hey, how about the Milky Way? Blah blah blah. Well, that's hard to say.
You're traveling through deep space, circling stars and entire galaxies. Whoa, looks like this multicolored nebula will soon collapse under its own weight and explode like a supernova. Now let's carefully circle this black hole. Try not to get caught in its gravitational field, or it'll swallow you like a space monster. Wait, what's that strange structure right there? It's a glowing wall. And if you look closely, each glowing dot is an entire galaxy. That wall has about 100,000 of these galaxies. The Milky Way has 100 billion stars. So this wall holds a quadrillion, that's 10 followed by 15 zeros, of stars like our sun. This giant structure is called the South Pole Wall. It's located about 500 million light-years from Earth. By comparison, the closest star to our home is Proxima Centauri, and it's about 4.2 light-years away. Rockets can cover that distance in about 73,000 years. So the journey to the South Pole Wall may take longer than our solar system exists. And this wall is simply gigantic, even on a cosmic scale. It's about 1.37 billion light-years long. To give you an idea of how large that is, the Milky Way is only 100,000 light-years wide. But you can't see this wall even with the most powerful telescope. The problem is that the Milky Way itself obstructs your view. It's so bright that it's hiding this wall. It's like trying to look at the starry sky in a metropolis. The light pollution won't let you do that. Scientists have been able to detect this galactic wall by measuring redshift. We know that all objects in the universe are moving. They spread out from each other as a result of the Big Bang, which happened billions of years ago. And when galaxies move, their light waves change slightly. By measuring this change, we can understand what the object is and how it moves. And this wall isn't even the largest in our universe. This is the Hercules Corona Borealis Great Wall. It's a giant flat superstructure about 10 billion light-years wide. That's around 10% of the entire observable universe. And it's also a wall. That is, a cluster of galaxies. We were able to detect this giant structure by gamma-ray bursts. It's the brightest electromagnetic event in the universe. You could even see it in the far reaches of our universe. Such bursts are a very rare event. In the Milky Way, for example, it happens once every few million years. If we notice many such bursts in a short time from the same place, it means that there are many objects like the Milky Way in that place. So, there are a lot of galaxies out there. Another unusual giant structure in the universe is the huge, large quasar group. It's about 4 billion light-years across. So it takes a photon of light almost as long as our planet has existed just to get from one side of the structure to the other. And if you put the huge, large quasar group on the scale, it would be 6.1 billion times heavier than our Sun. Scientists have found that there are at least 73 quasars in that structure. These are some of the most unusual objects in the universe. They are the active cores of galaxies. At the center of a quasar is a supermassive black hole. This giant eats up the matter around it. A wild force of gravity twists the matter around the black hole, forming a disk. And this disk is the source of the strongest radiation out there. By comparison, the radiation from a single quasar is tens or hundreds of times stronger than that of all the stars in our galaxy put together. Because of such strong radiation, we can detect quasars, even at very long distances. That's why they're also called beacons of the universe. Scientists use quasars to study the universe and the movement within it. One of the most distant quasars from us is about 13.1 billion light-years away. This makes it one of the oldest objects in the universe. It appeared about 690 million years after the Big Bang, and it's almost 3 times older than our solar system. It's still glowing with extreme brightness, about 4 and 14 zeros times brighter than the Sun. Scientists explain that at the center of the giant is a supermassive black hole, 800 million times heavier than the Sun. All these giant structures are just building blocks of our universe. Look, this is our solar system. Now, zoom out a little, and this is where our home star is in the Milky Way galaxy. Zoom out again. Here's a local group of galaxies. All the bright spots here are galaxies. Here's Andromeda, and here's the Triangulum galaxy, plus a few dozen other slightly smaller galaxies. They're all gravitationally connected. The size of this structure is about 10 million light-years. That's 100 times the width of our galaxy. Zoom out, please. This one is the Virgo supercluster. It's 20 times larger than the local group. There are about 30,000 different galaxies, and the mass of the whole thing is about 1 in 15 zeros solar masses. Zoom out again. Laniakea. This structure is almost 3 times larger. It includes the Virgo supercluster and other smaller clusters. And there are about 100,000 galaxies here. It's not over yet. Zoom out one more time. Here's the Pisces-Cetus supercluster complex. This giant galactic structure contains about 60 clusters of galaxies. So there are more galaxies in it than grains of sand in the desert. You know what to do. Zoom out! Phew! This is the observable universe. There are over 500 billion galaxies. And the stars? Well, there are about 1 billion trillion stars. The observable universe has its own structure. Clusters of galaxies form chains and walls, as you've seen before. But these strands are separated by huge regions of absolute emptiness. These areas are called voids. In these places, there is no matter at all. There are fewer molecules in the voids than in an empty room. One of these voids has a very mystical reputation. It's the Eridanus supervoid, or the cold spot. It appeared here only 380,000 years after the Big Bang. It's almost 1 billion light-years wide and could hold hundreds or thousands of galaxies with trillions of stars. Some scientists believe that this cold spot may have been the result of the largest collision ever, a collision of universes. There's a theory that our universe is some kind of bubble, a huge sphere that contains all these walls and chains of galaxies. Now imagine that there's an infinite number of these bubbles. They could be parallel worlds or different universes. Many years ago, one bubble came close to the bubble of our universe. Their walls touched, and the two universes connected for a while. It's like two drops of water coming together. But that universe kept moving. The area where the bubbles joined became thinner and thinner until that connection broke, and the two bubbles detached from each other. At this point, the second universe ripped some of the material out of our bubble. All those galaxies that used to fill the Eridanus supervoid ended up in a parallel universe. Scientists supposed we might travel through other bubbles. Flying to the supposed wall of our universe would take forever, and then it would take even longer to fly through interuniversal space. So we have to use portals, or wormholes. Here's how it works. Imagine a piece of paper with point A on one side and point B on the other. Instead of moving all the way across the sheet of paper, we just fold the sheet so that point A is right above point B. All that's left to do is make a small hole, and the journey takes only moments. Some scientists believe that such shortcuts through universes lie inside black holes. But how do you survive falling into a black hole? You just have to pick one that's big enough. It's all about gravity. Imagine you're falling into a black hole right now. The closer you get to it, the stronger effect it has on you. It intensifies with every inch. At one point, the gravitational force that affects your head is much stronger than the one that affects your feet. Then you turn into spaghetti. Yum. But if you choose a supermassive black hole, like the ones at the centers of galaxies, the gravitational force in them increases gradually. They can be millions of times heavier than the sun and much bigger, but the gravitational force on your head and your feet will be almost equal, and you will still feel comfortable. Who knows? Maybe if you manage to survive a fall into such a massive black hole, you'd find yourself in a completely different universe where different laws of physics apply. But so far, this is just a theory.
Recently, the James Webb Space Telescope has unearthed a mysterious ancient galaxy, and it might completely change our understanding of the nature of dark matter and the process of galaxy formation. The telescope has managed to spot a stellar population bigger than our home Milky Way galaxy from 11 billion years ago, and it shouldn't actually exist. This galaxy is massive and is home to extremely old stars. They formed in the early universe. The problem is that this new observation upends our current cosmological models, since, by the time of the galaxy's birth, not enough dark matter had built up to seed such a formation. Researchers have been chasing this particular galaxy for 7 years. They spent endless hours observing it with the help of the two largest telescopes on our planet to figure out how old it was. Unfortunately, it was too faint and too red, so no one could measure it. Only after scientists moved their observations to space and started using the James Webb Telescope did they manage to confirm the nature of the galaxy. The thing is, unlike the Hubble Space Telescope, which orbits around Earth, James Webb moves around the Sun 1 million miles away from Earth. That's why it made it possible to see the galaxy clearer. Previously, astronomers were sure that in early cosmic times, there were very few huge galaxies. But recent findings challenge these theoretical models. Extremely massive dormant galaxies have been discovered as early as 1 to 2 billion years after the Big Bang and the beginning of the universe. The scientist who led the spectral analysis of the James Webb Telescope data said that they were doing everything possible to confirm the oldest galaxies that existed deep in the universe. When they did, it pushed the boundaries of the current understanding of how galaxies form and evolve. And now, the main question is, how they managed to form so fast in the early universe, and what enigmatic mechanisms made them stop forming stars all of a sudden while the rest of the universe was still doing so. Galaxy formation is largely dictated by the concentration of dark matter. You see, around 84% of matter in the universe doesn't emit or absorb light. Astronomers call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. It supposedly affects visible matter, radiation, and the very structure of the universe. Finding extremely massive galaxies so early in the universe is posing serious challenges to our standard model of cosmology. All because astronomers don't think that such monstrous dark matter structures as the ones hosting those massive galaxies had enough time to form. Researchers need more time to figure out how common such ancient galaxies are and how massive they can be. But if they manage to find more of those, it will really upset our ideas of galaxy formation. But it could improve our understanding of the physics of dark matter. Bizarre ancient galaxies aren't the only thing discovered thanks to James Webb. For example, Scientists have long suspected that supermassive black holes could have existed in the early universe, and this theory has been proven only thanks to the JWST and its infrared eye. It showed that an ancient black hole within galaxy Sears 1019 was actively munching on all the matter it could lay its hands on. This hole is from the times when our universe was less than 600 million years old. And that's another mystery we're yet to crack. It's supposed to take way longer than 600 million years for a supermassive black hole to grow to its full potential. Astronomers were watching the galaxy hosting the unusually old black hole as part of the Cosmic Evolution Early Release Science Survey. They saw the galaxy as it was when our 13.8 billion-year-old universe was just 570 million years old. Besides the ancient black hole, scientists spotted two other ones. Those probably appeared 1 and 1.1 billion years after the Big Bang. They also discovered 11 ancient galaxies that existed between 470 and 675 million years after the beginning of cosmic history.
Bang! Or should I say, Big Bang. The Big Bang. Ahem. So, after the Big Bang, the universe resembled a hot soup of protons, neutrons, and electrons. After it started to cool down, the protons and neutrons began to combine, first forming ionized atoms of hydrogen and later some helium. These ionized atoms of helium and hydrogen attracted electrons, turning them into neutral atoms. As a result, the light was able to travel freely for the first time ever, since it was no longer scattering off free electrons. What does it mean? The universe was no longer dark. At the same time, it was still about a few 100 million years after the Big Bang before the very first sources of light started to appear. That's when the cosmic dark ages came to an end. We don't know for sure what this universe's first light looked like or how the first stars formed. Luckily, we have the James Webb Space Telescope to help us find the answers. How come? All because this is an infrared telescope. Why is it important? Let's figure it out. Imagine a star. It's a very, very old star, maybe the first star out there. Light leaves this star 13.6 billion years ago and settles off on an incredible journey through space and time. It needs to get to our telescopes. By the time this light reaches us, its color or wavelength shifts towards red. That's something we call a redshift. It happens because when we talk about very distant objects, Einstein's theory of general relativity comes into play. According to it, the expansion of the universe also means that the space between objects stretches, making them move away from one another. But that's not all. Light stretches too, which shifts it to longer wavelengths. Eventually, this light reaches us as infrared. In other words, redshift means that light that is originally emitted by the first stars or galaxies as ultraviolet or visible light gets shifted to redder wavelengths by the time we catch a glimpse of it here and now. For the farthest objects with very high redshift, that bare minimum of visible light is shifted into the near and mid-infrared part of the electromagnetic spectrum. That's why to see those space objects, we need a super powerful telescope. And if we talk about the Webb telescope, it can see back to about 100 million to 250 million years after the Big Bang, which is incredibly awesome. So by observing the universe at infrared wavelength, James Webb lets us see things no other telescope has ever shown before. The primary goal of this incredible piece of equipment is to study the formation of galaxies and stars that formed in the early universe. To look that far back in time, we need to look deeper into space. All because it takes light time to travel back from there to us. So the farther we look, the further we glimpse back in time. To find the first galaxies, James Webb is going to make an ultra-deep near-infrared survey of the universe. Then it'll follow it up with a few other methods of research. Now, as you remember, the gas between stars and galaxies in the early universe was opaque, and energetic starlight couldn't penetrate it. But then, about 1 billion years after the Big Bang, it suddenly became completely transparent. Why? The James Webb Telescope might have found the reason. At one point in the past, the first galaxy's stars emitted enough light to ionize and heat the gas around them. This helped clear the view over hundreds of millions of years. The newest insights scientists got were about a time period called the era of reionization. That's when the universe underwent some dramatic changes. After the Big Bang, gas in the universe was unbelievably hot and dense. Hundreds of millions of years passed, and it cooled down. But then, something baffling happened. It was as if the universe hit the repeat button, and the gas became ionized and hot once again. It could have happened because of the formation of early stars. After that, millions of years later, this concoction became transparent. For a long time, researchers have been hoping to find definite evidence that could explain these changes. And now, the telescope has finally shown that those transparent regions are located around galaxies. Astronomers have seen these galaxies reionize the gas surrounding them. Even better, they've managed to measure how large these transparent regions are. They're ginormous compared to the galaxies themselves. Imagine a hot air balloon, and now imagine a pea floating inside. You've got it, and guess what? These tiny galaxies drove the entire reionization process, clearing huge regions of space around them. These transparent bubbles kept growing until they merged and caused the entire universe to become transparent. The research team chose to target a period of time before the end of the era of reionization. At that time, the universe was not quite opaque, but not quite clear either. It was a patchwork of regions of gas in different states. To find out this cool fact, the astronomers aimed the James Webb telescope in the direction of a quasar, an incredibly bright space object. It acted as a giant flashlight, traveling towards us through different regions of gas. It was either absorbed by the patches of near opaque or moved freely through the areas where the gas was transparent. The scientists then used Webb to examine galaxies in that region of space. They found out that these galaxies were usually surrounded by transparent regions with a radius of about 2 million light-years. For comparison, the area the galaxies cleared was almost the same distance as the space between our home Milky Way galaxy and our nearest neighbor, the Andromeda galaxy. And the telescope witnessed those galaxies in the process of clearing the space around them. It was the end of the era of reionization. Until then, no one had evidence of what caused reionization. The team is planning to dive into research about other galaxies in 5 additional fields. The Webb telescope's results from the first field have been overwhelmingly clear. And even though the astronomers had expected to identify a few dozen galaxies existing during the era of reionization, they actually managed to spot 117. Now, let's talk a bit about the main hero of today's show, the James Webb Space Telescope. It's an absolutely stunning piece of equipment which is around 100 times more powerful than the Hubble Space Telescope. And the latter has observed places that are 13.4 billion light-years away. The James Webb Telescope is also on the pricey side, to put it mildly. Even though originally the cost of the telescope was estimated to be just $1 to $3.5 billion. The whole development process cost around $10 billion. For comparison, it cost NASA $4.7 billion to build and launch the Hubble telescope, and it was another $1.1 billion to fix it in orbit. Even though the James Webb Telescope itself is 3 stories high and the size of a tennis court, its mirrors are the lightest large telescope mirrors of all time. During the manufacturing process, they underwent a 92% reduction in weight. When you look at them, the telescope's mirrors seem to be gold, but in reality, they're made of beryllium. This is a steel gray, lightweight, and brittle metal. A gold coating is applied to each mirror, that's true, but they can't be produced entirely out of gold, since this precious metal tends to expand and contract, even with small temperature changes. So the total amount of gold in the James Webb Space Telescope is less than 2 ounces. That's a golf ball-sized piece of gold. and the gold plates covering the mirror are less than 1,000 atoms thick. As for the telescope's abilities, it would be able to clearly see a US penny from 24 miles away and a football from 340 miles away. James Webb's telescope side is cooling itself down, and its temperature doesn't rise higher than minus 370 degrees Fahrenheit. That's cool enough to make liquid nitrogen. A truly enormous 5-layered sun shield surrounds the telescope and reflects away as much sunlight as possible, letting the telescope stay cool.
You're traveling through space, trying to get through an especially rough patch. You gotta dodge asteroids, space debris, wandering black holes. No, it's not an episode of a sci-fi series, at least not completely. For the first time ever, astronomers have found a black hole that's completely alone, drifting through space with no stars or planets nearby. This black hole is about 5,000 light-years away from us in our own Milky Way galaxy. Do we need to look for a hero with superpowers to save Earth? First things first, a black hole is a place in space where gravity pulls so much that nothing, not even light, can get out of this region. The gravity is so strong there because a huge amount of matter is squeezed into a tiny space. Supermassive black holes, hundreds of thousands to billions of times the mass of our Sun, are often found at the centers of galaxies. Most of them stay put or move at a very, very slow pace. But the newly discovered black hole is much weirder than anything we've seen before. First of all, it tries to avoid commitment. It's lonely, with no companion star or home galaxy. An even stranger thing is that it's zooming through space at a speed of 31 miles per second. What might be the reason for this speedy cosmic journey? Let's look at the following imaginary scenario. One day, a really massive star exploded in a supernova. It was the very star that formed our black hole. The resulting blast gave the new black hole a massive kick and sent it flying through the galaxy, starting its unbelievable voyage. Now, it's only one of a few possible explanations, but it sounds quite plausible. I bet you can't help but think, what if this wandering black hole decides to visit our solar system? Are we doomed? Scientists tell you to relax and breathe out. This black hole is very far away, and your chances of ever encountering it are infinitesimal, if any. Plus, this black hole is totally quiet and dark at the moment. One day, it might wake up and start glowing. It'll happen if it begins to eat something. In the near future, powerful new telescopes may find many more wandering black holes like this one. Usually, black holes are super hard to find because they don't give off any light. You can only detect them when they're eating nearby matter. That makes them glow brightly. Or when they have a companion star. In this case, it moves in a strange way, which gives away the presence of a black hole. But this newly discovered black hole is lonely, totally by itself. There's no glowing, no companion star moving hectically. So, how did scientists spot our cosmic wanderer? They used something called gravitational microlensing. That's when the black hole's gravity bends and magnifies the light from a star located behind it, kind of like using a magnifying glass, hence the name. This method allowed scientists to detect the black hole even though it was completely dark. All in all, black holes are fascinating things, and some of them are truly unique, like these biggest black holes ever found. You see, almost every galaxy has a supermassive black hole at its center. They're huge, with masses millions to billions of times bigger than our Sun. One of those is called TUN 618. It's a really huge and powerful black hole that's part of something called a quasar, a super bright spot in space emitting incredible amounts of energy. TUN 618 is very, very far away, about 18.2 billion light-years from Earth. And it's 40 billion times heavier than our Sun. There are also black holes that feed on their own kind. Black holes are known for devouring anything that gets too close. And this anything can include not only stars and gas, but also other black holes. Scientists witnessed a ginormous black hole at the heart of one galaxy being swallowed by an even larger black hole in another galaxy. It was the first time we detected such an event. The discovery was made using NASA's Chandra X-ray Observatory. One black hole weighs about 30 million times the mass of the Sun, while the other has at least 1 million times the mass of the Sun. Then, there is a bullet-shooting black hole. Apparently, black holes don't just swallow matter, they can also shoot it out. For example, astronomers studied one relatively small black hole, which is about 28,000 light-years from Earth and weighs between 5 to 10 times the mass of the Sun. And they saw how this black hole pulled matter off a companion star and then blasted some of it out in the form of huge bullets of gas. These bullets are super fast. They move at nearly a quarter the speed of light. Some black holes spin incredibly fast, twisting space around them at extreme speeds. One example is a black hole located in the constellation Agila, about 35,000 light-years from Earth. This black hole spins at a staggering speed of more than 950 times per second. If you could place an object on the edge of this black hole's event horizon, it would spin around the black hole at 333 million miles per hour. That's nearly half the speed of light. The smallest black hole discovered so far has been nicknamed the Unicorn. Located 1,500 light-years away from Earth, it's around 3 times the mass of our Sun. This makes it very close to the smallest possible size for a stable black hole. While black holes themselves are far away and difficult to study directly, scientists find new clever ways to study their properties right here on Earth. They've been able to recreate certain features of black holes in the lab. For example, black holes have a gravitational pull so strong that nothing, including light, can escape once it crosses the event horizon. To understand this better, researchers have created an artificial event horizon using fiber optics. They've also been able to simulate Hawking radiation, the kind that likely escapes black holes, by setting up experiments in the lab. These lab-created mini black holes help scientists understand the mysterious properties of real black holes. There are several types of black holes, and each of them is born in its own unique way. Primordial black holes are believed to have formed right after the Big Bang, when the universe was very young. Stellar black holes form when a massive star collapses in on itself. This causes a supernova, where the outer layers of the star explode into space, and the core turns into a black hole. As for supermassive black holes, they're thought to have formed alongside the galaxies they're in. The size of the black hole is usually related to the size and mass of the galaxy. Despite what many believe, black holes don't roam the universe randomly, looking to swallow planets. They obey gravity like anything else in space. So, for a black hole to affect Earth, it would have to be very close, much closer than any black hole is to us right now. Even if a black hole the same mass as the Sun replaced our Sun, Earth wouldn't fall into it. The black hole would still have the same gravity as the Sun, and Earth would continue orbiting it just like it orbits the Sun today. It would get much colder though, so we wouldn't survive such a replacement in any case. But don't worry, our Sun will never turn into a black hole. It doesn't have enough mass to do so. Instead, in about 5 billion years, when the Sun reaches the end of its life, it will become a red giant star. After using up its fuel, it will shed its outer layers, creating a glowing ring of gas called a planetary nebula. What's left will be a cooling white dwarf star.
Is there a giant mega-sun in the center of our Milky Way? Scientists actually thought so for a while because it's the brightest place in the galaxy. It has millions of stars packed into a small area. This area is called the Gigantic Bulge. The Gigantic Bulge has millions more stars per light-year than any other part of the galaxy. It can be 10 million times denser than our part of the neighborhood. In some cases, stars in this region are only 5 light days apart. That's like if there was another star in our solar system a bit further away than Pluto on a space scale. But why is this place so dense? When galaxies form, a lot of gas and dust come together under the force of gravity. This material gathers up and eventually forms stars. Gravity and angular momentum balance out, and it starts looking like a flat disk with a pretty bright, bulging, dense core. The stars live their comfy lives, and once they get to the finishing line, they collapse under their own huge weight. Then, the black hole forms. Black holes love to eat everything around them, and the more they eat, the bigger they get. And what place is more perfect for a fine dinner than the galaxy's center, where all the space stuff is packed together? So it starts eating surrounding gas and dust, forming an accretion disk. As this material spirals into the black hole, it heats up and emits a lot of energy, which makes the center of the galaxy even brighter. That's why you can find both supermassive black holes and galactic bulges in the centers of all galaxies. The galactic bulge at the center of the Milky Way looks a bit like an ellipse. That's a classical bulge. Stars aren't like our sun. They move randomly in all possible directions and planes. Plus, they all move at different speeds. So gravity is going crazy there, and this makes the bulge look more like a sphere, or an ellipse. Since they were the first ones to form, they have some of the most ancient stars in our galaxy. But there are also some places of star formations and lots of younger, massive stars that are less than 100 million years old. As we move farther away from the center, things get a bit calmer. Stars start rotating uniformly and become stable. Right now, Earth is in one of the Milky Way's spiral arms called the Orion Arm, pretty far away from the galactic bulge. In our part of the neighborhood, stars are usually about 4 or 5 light years apart. This means that most of a galaxy is actually just black, empty space. Our black hole is called Sagittarius A star. It's a monster about 4 million times the mass of our Sun. It's also about 32 million miles in size, almost like the distance between Mercury and the Sun. But don't worry, it's not attracting the Milky Way inside it, and it's not going to eat us. These black holes are actually super small compared to the entire galaxy, so they can only eat whatever's around. Right now, many stars orbit Sagittarius A star. And even though it emits a huge amount of energy, we can't see its light from Earth without a lot of scientific effort. But why don't we see the center itself? The galactic bulge is so bright that even though it's 26,000 light years away, we should see it shining brightly in our sky. Yet we don't. Turns out it's all because of space dust. There's a lot of dust between us and the core, and it absorbs most of the visible light. We can only look at the galactic core using other types of light, like near-infrared, gamma ray, and so on. NASA has images of the core in different types of light, and it shows how scarily bright the center is without the dust blocking our view. But not all bright regions are blocked by gas and dust. For example, when we look at dense clusters like the Messier 13, the stars are so close together that they look just like a white spot. Most of our telescopes can't separate them from each other. The satellite galaxy M32, our neighbor near the Andromeda galaxy, has about 84 stars per light year. It's so dense that stars can't be resolved even by the Hubble Space Telescope. To get the idea, our solar system is 2 light years long. We'd see about 168 stars outside our window if we were there. Our closest star is Alpha Centauri. It's about 4 light years away from the Sun. If it was just a couple of light days away, it would shine much brighter than the full moon. So if we somehow managed to survive in crazily dense star regions, the sky would be white all day long. But it's unlikely that we'd make it. As we get closer to the center of the Milky Way, the chances of finding life get super slim. The gravity of stars is going wild with chaotic movements, so there are barely any planets around. On those miracle planets, the radiation from cosmic rays is skyrocketing. Supernova blasts and star collisions nearby become an everyday occasion, and all the gas around makes it basically impossible to breathe or even see properly. At the same time, as we move further away, there are fewer stars around. Elements that are super useful for life, like carbon, oxygen, and iron, are produced by stars, so they also drop. Too much radiation is awful, but too low radiation means that there's not enough energy to support chemical reactions, like photosynthesis. Which is why, if there is extraterrestrial life, it would most likely be somewhere in the middle of different galaxies. But some galaxies get their brightness from a so-called active galactic nucleus. These are extremely energetic regions at the center of some galaxies. They shine much brighter than any stars imaginable, although it mostly shines only in certain parts of the electromagnetic spectrum. The brightness comes not from the stars, but from the accretion disk around their supermassive black holes. As the material slowly falls into a black hole, it gathers around it and creates this flat, spinning disk of gas, dust, and other stuff. Since the gravity and friction there are insane, this disk heats up and starts emitting enormous amounts of energy. Also, this disk spins incredibly fast, almost at the speed of light. Because of that, collisions there happen all the time, and they're unimaginably powerful. They release even bigger amounts of energy. Most galaxies don't have an AGN. Those that do, like the galaxy M87 in the Virgo constellation, are called active galaxies. There are also different types of AGNs: the Seyfert galaxies, radio galaxies, and finally, the winners of our space brightness competition, Quasars. Imagine things so bright that they can outshine the entire galaxy they belong to. Quasars are a specific type of active galactic nucleus, the most extreme and luminous form. They belong to the supermassive black holes, the biggest ones in our universe. Quasars are like a combination of several things. First, they're the brightest accretion disks in our world, because of their behemoth black holes eating everything around. But they have some cool features. For example, they have powerful jets of particles that shoot out from the poles of the black hole at nearly the speed of light. These jets add up to the brightness of the quasar, although they can only be seen in radio wavelengths. The energy they emit is so intense that they can be seen billions of light years away. However, the nearest quasar to us is 600 million light years away, so we can't see them with backyard telescopes. So, when we look at a galaxy through a telescope, we usually see only the brighter core, not the outer parts. Unfortunately, our eyes just aren't made to see things like the active galactic nucleus. So, these stars are the brightest things we can see. But what a beautiful sight it is.
Our universe is like a giant highway, and galaxies are constantly moving along this highway. And just like cars driven by careless drivers, they can collide and crash. So, astronomers have recently witnessed such an incredible cosmic collision. It involved galaxies traveling at incredible speeds. Using advanced instruments, researchers clocked one galaxy traveling at a speed of around 2 million miles per hour as it crashed into a group of other galaxies. This collision has created shock waves that are so powerful they can completely reshape the entire region, leaving long-lasting effects on its structure and dynamics. Will it somehow influence our solar system? Before we find out, let's learn more about the region where this collision occurred. Actually, this collision is still happening in Stephan's Quintet. That's a fascinating cluster of galaxies that has been the subject of study for scientists for over a century. It's a group of 5 galaxies located in the constellation Pegasus. This group of galaxies was first discovered in 1877 by the French astronomer Édouard Stephan, who used a telescope at the Marseille Observatory. Despite its tranquil name, Stephan's Quintet is anything but peaceful. It's a chaotic spot filled with galactic collisions and turbulence. 4 out of the 5 galaxies are gravitationally bound. It means they are physically interacting with one another. Such interactions are ejecting material from the galaxies, and over time, it forms vast debris fields in the space surrounding the galaxies. Astronomers believe that, in the end, These galaxies will merge into one giant galaxy, but it will only happen in millions of years. The curious thing, though, is that the fifth galaxy in the Quintet, located in the upper left corner of images, is not part of the collision. This galaxy is much closer to Earth, more than 200 million light-years closer, to be precise. So its alignment with the other galaxies is just a chance perspective from our vantage point, making it appear as part of the group. Stephan couldn't know this in the 19th century, so the name Quintet has remained, even though only 4 galaxies are physically involved in the collision. Now, how about we look at this collision in detail? At the center of this event is one of the galaxies in the group, which is currently crashing into the others at a breathtaking speed. From our perspective on Earth, this galaxy appears to be approaching the Quintet from behind, heading directly toward the viewer. The collision is creating a massive shockwave that ripples through the surrounding galaxies. As the shockwave is moving through packets of cold gas, it's traveling at hypersonic speeds, several times the speed of sound in the intergalactic medium. This process strips electrons from atoms, leaving behind long trails of glowing ionized gas. But when the shockwave comes across regions of hot gas, it compresses the material rather than disrupting it. This compression produces radio waves, which can be detected by radio telescopes. While reshaping the structure of the intergalactic medium in Stephan's Quintet, this shockwave also influences the future evolution of the galaxies involved. Now, how did scientists even manage to spot such a dramatic space event? All thanks to innovative technologies. The most important participant was Webb, a cutting-edge spectrograph that's installed on the William Herschel telescope in La Palma, Spain. This tool specializes in gathering spectroscopic data, which is the information about how matter absorbs or sends out light and radiation. It allows astronomers to examine the movement and composition of space objects with great precision. Besides Webb, researchers have used data received from a few other large observatories. One of those was LOFAR, Low Frequency Array. It's a radio telescope with an antenna network observing the radio waves the weaker shock wave produced while compressing hot gas. Astronomers combined the data received from all these instruments and managed to study the shock waves and their effects in amazing detail. This collision in Stephan's Quintet gives us a fantastic opportunity to find out more about the interactions between galaxies, which can influence the evolution of the universe. You see, when galaxies crash into each other, their gas and dust gets redistributed, and it can trigger the formation of new stars and even cause central supermassive black holes to grow. And if we talk about Stephan's Quintet, the ongoing collision in this area helps us get additional information about the behavior of gas under extreme conditions. Now, at the same time, galactic collisions aren't as rare as you might think. They're common on a cosmic scale, and in the early universe, collisions occurred even more frequently because galaxies were located much closer together. With time, such interactions have played a key role in shaping the universe. Even our own galaxy, the Milky Way, has experienced tons of past collisions. We can see the evidence of such destructive interactions in the form of debris streams and disrupted star clusters within the galaxy. In fact, astronomers predict that the Milky Way will collide with the neighboring Andromeda galaxy in about 4.5 billion years, eventually forming a new, larger galaxy. Even though they're moving at incredible speeds, galactic collisions are super slow processes from our human point of view. While galaxies may travel at millions of miles per hour, the distances they cover are so vast that mergers take millions to billions of years to complete. Now, galactic collisions don't look like explosive crashes you might be imagining. Instead, they resemble when fluid merges. When two galaxies collide, their gravitational forces distort their shapes. They stretch and warp, and exchange their material, stars, gas, and dust. As a result, tidal tails, rings, and even bridges between galaxies form. One of the most famous collisions between galaxies is ARP 148. During this cosmic crash, one galaxy became shaped like a ring, while the other stretched in a long tail-like form. That's how powerful gravitational interactions between galaxies during collisions are. But however impressive intergalactic collisions are, collisions between neutron stars, those ultra-dense remnants of massive stars, are among the most energetic phenomena in the universe. Neutron stars are incredibly small and dense. Just one contains the mass of our Sun packed into an area the size of a city. When two neutron stars collide, they often merge to form a black hole, releasing immense amounts of energy in the process. These events produce gravitational waves, ripples in space-time, that can be detected by instruments like LIGO and Virgo, as well as bursts of light that outshine billions of stars. On Earth, the possibility of a galactic collision directly affecting us is extremely low. Luckily, the timescales and distances involved make such events harmless to life on our planet. However, smaller-scale collisions, such as an asteroid impact, are more plausible. Asteroid impacts have occurred in Earth's history, and the most infamous of them caused the extinction of the dinosaurs 66 million years ago. And while large impacts are rare, astronomers closely monitor near-Earth objects to protect our planet from potential threats. Now, while we're talking about space collisions, a question may arise. Can life travel between planets? This is the idea of lithopanspermia, the transfer of life between planets via debris from collisions. If an asteroid or comet hits a planet, fragments of rock could be ejected into space. If those fragments carry microbial life, they might land on another planet and seed life there. And guess what? According to experiments, certain super tough microorganisms like cyanobacteria could survive the harsh conditions of space travel, including radiation and re-entry into the atmosphere of another planet. In any case, lithopanspermia is still only a theory and a controversial one among scientists, but it doesn't make it less fascinating. It might eventually help us understand how life could have spread across the universe. But let's return to the ongoing collision in Stephan's Quintet. By studying such events, astronomers learn more about how galaxies interact, evolve, and influence their surroundings. Hopefully soon, we'll find even more interesting facts about this process. Stay tuned.
During the recent years, scientists made 2 breakthrough discoveries about our universe. Thanks to new technologies, we've looked into the distant past. And we've learned something that can change our understanding of the universe forever. What are these discoveries and what do they mean to us? Let's find out. Recently, we unveiled the first color image from the James Webb Space Telescope. It's a mind-bending photo capturing thousands of ancient galaxies. This oldest documented light in the history of the universe dates back over 13 billion years. That's just 600 million years after the Big Bang. It's like getting a sneak peek into the universe's baby album. But that was just the beginning. Astronomers were expecting to see some tiny young galaxies. But what they found was a real surprise. Impossibly early, impossibly massive, and all that from just a tiny red dot. The lead author of the study, Ivo Laba, was working at the computer as usual, and suddenly he got 2 numbers. Age, 13 billion years. Weight, 100 billion stars. When he realized what that meant, he nearly spit out his coffee. But that red dot was just the beginning. The next day they found 5 more galaxies just like this. Turns out, these 6 massive galaxies are as old as the Milky Way itself. The entire research team was in disbelief. They were like, wait, what? These guys couldn't be that mature so early in time. Did we make a mistake? But nope. The James Webb Space Telescope, the new cool guy on the space block, just has some serious skills. It can see through dust clouds with its infrared vision and spot galaxies that were previously invisible. Move over Hubble. There's a new stargazer in town. But why is it shaking things up so much? Because this discovery affects our understanding of how galaxies formed. Let's try to explain. A long time ago, 13.8 billion years ago to be precise, our universe was born. It was chilling out for a while, and then it started to form the first galaxies. And these galaxies were full of gas and dust. Eventually, this gas started turning into stars. Some galaxies were more massive and had more stars, and some were lighter and had almost no stars at all. In any case, they all grew gradually. The stars in them were born slowly and smoothly. That's how our current models explain this. But these new observations from the James Webb Space Telescope show an unexpected surprise. Looks like Even in the early universe, our ancient friends had lots of stars. More than what we would ever expect. If that's the case, then these galaxies are like the overachievers of the universe. They skipped the small and gradual growth phase and went straight to being giant universe breakers. According to our current cosmological model, they shouldn't even exist. But they do, so it looks like after the Big Bang, the stars were forming much faster than we thought, which is pretty weird. This could mean that there's something missing in our understanding of the galaxy formation. As you can see, these universe breakers are really living up to their name, causing a potential total consensus among scientists. The universe was like, hey, I'm about to flip cosmology models upside down. But let's not jump to conclusions. There are many theories that could explain these mind-boggling discoveries without breaking the standard model. For example, maybe the light we're seeing isn't coming from stars at all, but from the swirling disks of doom around supermassive black holes. These colossal cosmic beasts can gobble up matter and spit out a dazzling light show. And James Webb Telescope's keen eye is picking up on these enigmatic accretion disks like never before. Or maybe these galaxies could be playing hide-and-seek with us. Maybe there's more to the story that we haven't seen yet. After all, the universe is vast and mysterious, and we've only just begun to scratch the surface. And whoa, we really need to slow down here. Before we even try to explain all this stuff, we need to confirm whether these ancient galaxies really are that old. Although even if they're actually just supermassive black holes, it still shows an astounding change. We'll have to wait about a year to find out. One thing's for sure, the James Webb Space Telescope has definitely taught us a valuable lesson. Expect the unexpected. And this is just the beginning of unexpected. Ivo Laba's team wasn't the only one who made such a huge breakthrough. There's also a team that claims that they've unlocked the secrets of the universe's past, and that's worth 2 Nobel Prizes. Move over James Webb Space Telescope, because this discovery came from an antenna that's smaller than a fridge and costs less than $5 million. Talk about space bargain hunting! The astronomers caught this signal that showed some surprises. It was coming from the earliest stars of our universe, back in the days when they were just beginning to twinkle. Say hi to our celestial ancestors again. Now, the signal was pretty weird. The temperatures were unusually low, and there was a pronounced wave that left astronomers scratching their heads. What could be causing all this? Well, there's a theory. Dark matter may have been at work, and if that's the case, then we can really be on the verge of a great discovery. Imagine you're looking at the night sky filled with stars, but there's something else there that you can't see. It's like an invisible cloak that covers the entire universe. Scientists call this mysterious stuff dark matter. Dark matter is like the ghost of our world. It doesn't emit, absorb, or reflect any light. We can't see it with telescopes or our eyes. That's why we call it dark matter. But if we can't detect it in any way, how do we know it exists? Because of its gravitational pull. One day we noticed that our understanding of how galaxies were created was incorrect. According to our calculations, they should have been some chaotic gas, but something held them together, turning them into spirals, like some kind of invisible glue. Then we thought, maybe this invisible glue really exists. If the moon was invisible, we would still suspect that it exists somewhere because its gravity affects the tides on Earth. This is also the case with dark matter. Its gravity influences the motion of galaxies and other cosmic objects. In fact, dark matter makes up a huge chunk of the universe, about 27% of it. Moreover, the normal matter we can see, like stars, planets, and galaxies, only make up about 5% of the universe. So even though we can't see dark matter, there's actually more of it in the universe than everything we can see. Scientists are still trying to figure out if dark matter exists and what it can be made of. Some theories suggest that it could be made up of exotic particles that are different from the particles that we're used to. Others think that it might be some kind of weird, undiscovered form of matter that doesn't interact with light at all. Anyway, it's an intriguing mystery, and if we ever confirm the existence of dark matter, our understanding of our world will change forever. So now you can understand why the excitement in the scientific community is palpable. If this discovery is confirmed, then we will get the first real proof of dark matter. This discovery may be even more important than the Big Bang itself because, as astronomers put it, We are made of star stuff, and so we are glimpsing at our origin. But of course, we still have to wait and explore all this in great detail. In science, one should never rush to conclusions. And while scientists study this stuff, we'll be here, on the edge of our seats waiting for the next space blockbuster to unfold. The universe never ceases to amaze us with its wonders. Who knew that such a small and humble antenna could unlock such cosmic secrets? It just goes to show that in the vastness of space, even the tiniest discoveries can have the biggest impact. Keep looking up, and who knows what other cosmic surprises are waiting to be uncovered.
Look up when the sky is clear at night. You'll see thousands of tiny bright dots there. It may seem like they're fixed in one spot, but in reality, they're constantly moving. In 100,000 years, there won't be a constellation with the same shape or pattern we know today. And think about all those red dwarfs, small stars, planets, space bodies we can't see with the unaided eye. Red dwarf stars are especially cool. They're usually about half the size of our sun, and mostly 1/10 as bright. They may not be the brightest things in the sky, but they live for a very, very long time. Nuclear fusion reactions happen deep in star cores. That's what makes them shine. Large stars release huge amounts of energy, burning their stellar fuel. But such stars tend to burn all their fuel in only a couple of million years. Stars like our sun usually live for about 10 billion years, but red dwarfs don't use that much of their fuel. Their light is not so powerful, and they don't require much energy to support their existence. They're like energy-efficient cars. That's why they can last hundreds of billions of years. Some of the smallest ones may live for up to 10 trillion years. Most hydrogen in sun-like stars remains unspent. There's more of this gas in the atmosphere rather than in the core of such stars. This means most hydrogen doesn't take part in the fusion reactions. But it's different with red dwarfs. They circulate plasma throughout their entire bodies. These stars pull fresh hydrogen reserves from their outer layers into their core. That's what keeps fusion reactions running. One day, in the distant future, stars like our sun will run out of fuel and shut down. The universe will be full of small red dwarfs. They won't have enough energy to shine and brighten the space around them. Our descendants, if there are any, will inherit a dim, dark cosmos. As it gets older, the sun will balloon to a size where it will destroy nearby planets. First Mercury, then Venus, and then us. On the other hand, Earth will probably survive, but barely and not for long. The sun will burn it to a crisp when it gets closer. The outer planets of our solar system will also survive, but they'll move even farther away into space. The sun will lose some of its mass while increasing in size. Its gravitational pull establishes the orbits of the planets. When our star becomes less massive, the pull of its gravity will become weaker, and the outer planets won't have such a strong connection with the sun. Our solar system is not isolated. There are many other stars in our galaxy. Within 30 billion years, stars that travel nearby will mess with our outer planets, enough to rapidly launch some of the biggest ones out of the solar system altogether. The last planet to stay will stick around for a while longer, maybe even 100 billion years. But even that one will eventually end up kicked out of the solar system. There's a theory claiming that we got most of the water on our planet from ice-laden meteorites and comets, frozen balls of ice and dust. As they crashed into the early Earth, they probably brought water, which was necessary to develop life. But those very same objects that might have created life on our planet could also be its end. This is not a matter of if, more a matter of when. And scientists think it's very likely that an asteroid or comet big enough to wipe out life on Earth will smash into our planet. But it'll happen in the distant future. And fortunately, we have the technology to predict such things and react on time. But there are other cosmic collisions we can't avoid, no matter what we do. Andromeda, our neighboring galaxy, is moving toward the solar system at a speed of 68 miles per second. There are 2.5 million light-years between the Milky Way and Andromeda, so luckily our neighbor won't cover that distance anytime soon. It'll only happen in around 4 billion years. Such a collision of two galaxies might lead to real chaos for our descendants, if any of them are still living on Earth, that is. The two galaxies will slide past each other. Then they'll draw apart until the gravitational force starts pulling them back together. As they merge, they'll both lose their disk-like structure and form one big elliptical galaxy. It's already got the nickname Milkomeda. The Milky Way as we know it today won't exist anymore. Space is in constant motion, changing all the time. Scientists have a couple of possible scenarios of what might happen with the universe in the future. Number 1, the Big Rip. This theory claims that the universe will expand infinitely. At one point, the pull of the expansion will get stronger than the gravitational force keeping it all together. If this happens, it will tear apart galaxies, stars, black holes, and all other space bodies, including Earth. The universe will turn into a bunch of disconnected particles. Until about 5 billion years ago, the universe was expanding slowly because of its powerful gravitational pull. Then its growth sped up. Some experts say it happened because of the effects of dark energy. Dark energy is a mysterious force that makes up almost 70% of our universe. This force pushes it to expand faster rather than slowing it down. So, in the case of the Big Rip scenario, dark energy will win over gravity to the point where it will be able to rip apart individual atoms. Scenario number 2, the Big Crunch. There's a possibility the universe will get to the point where it'll stop expanding. Gravity will become a dominant force. It might even reverse the expansion of the universe. Then, the cosmos will start shrinking, making planets, stars, and even entire galaxies collide. In the end, the whole universe will collapse in on itself. Once everything compresses into one infinitely small point, which is something called the Big Crunch, the universe may start expanding once again. Theory number 3, the Big Freeze. Brr. In this scenario, entropy will grow until it reaches its maximum value. Entropy is basically the idea that everything in the universe declines into disorder at some point. Once entropy gets to its maximum, the heat in the system will be spread evenly. The universe will then disappear because there won't be any room for heat to exist. Any mechanical motion inside the universe will stop. The cosmos will be so empty and gas will be so thin that no new stars will be able to form or shine again. In such a cosmos, time is just an endless void. Nothing ever happens with planets, stars, or living beings. The entire universe is frozen, dark, and motionless because there's no energy that can make things start working again. Many, many billions of years after the last stars burn out and fade, black holes will send a message that the universe has come to an end. Black holes are areas with extremely strong gravitational pull, so powerful that nothing can escape it. They can be as massive as 100 suns. As for supermassive black holes, their mass can be greater than that of 1 billion suns. You can find such giant black holes at the center of most galaxies. Like everything else, black holes will experience the same end. But when their moment comes, they won't gently disappear into the night. Black holes will go away in enormous bursts of fireworks, lighting up the universe in the last moments of their existence. It will be the end of the entire era. Black holes usually survive by gobbling down the stars and gas that come close enough. Their gluttony is the main feature that gives them away. In most cases, there's an accretion disk around a black hole. That disk is made of all those materials and particles it's torn apart and is pulling inside, similar to when water swirls down a drain. As the materials and particles draw closer, they start to move faster and faster. This generates heat, which makes the accretion disk glow, which again gives away the black hole. Yep, black holes aren't that great at hide and seek. Things that cross a black hole's event horizon, which is also called the point of no return, are lost forever. But Stephen Hawking had a theory that you might be able to escape from a black hole. There are particles moving even in a vacuum. Let's say one particle has positive and one has negative energy. If they both come close to a black hole, there's a chance that one will fall into it while the other will escape. That means the black hole has radiated the particle away. And this particle has taken some of the black hole's mass with it, which is why the black hole may start shrinking. As it begins to evaporate, it loses its mass and slowly becomes smaller. More and more particles start leaving until all the energy that's left behind escapes all at once. In the final tenth of a second, there will be a giant flash of energy and light in a very, very small region of space. And then, it's all gone. 13.8 billion years ago, a mysterious explosion happened in space. It was chaos, a time when the stars, planets, asteroids, the rest of the space bodies, and galaxies were born. It was the Big Bang, a theory we all know about. But no one knows for sure what happened, where the universe came from, and what was there before. Some even think the universe went through a cycle where it contracted and expanded several times. In 1991, a cosmologist from Stanford University named Andre Linde had submitted an article with the main idea that there was a possibility the universe had been created in a laboratory. His theory said there was a chance an advanced civilization somewhere out there had created our universe. This civilization has made an entirely new cosmos that later evolved its own planets, stars, and intelligent forms of life. 30 years later, many scientists take this theory pretty seriously. They even started talking about things that we, as a civilization, can do to get to such an advanced level. The theory says this advanced civilization decided to add technology that helped to create a new universe out of nothing. It happened through quantum tunneling. It's when an atom can appear on the opposite side of some barrier, even though it's supposed to be impossible, considering the laws of physics of our world. Like if you wanted to pass a tall wall, but you can't pass it with ladders or go around somewhere. Imagine you can just walk through it like a ghost. In our world, it's not possible, but a more advanced civilization perhaps can do it. Plus, they realized how they could create new universes. Right now, on the cosmic scale, we could be a Class C civilization. We don't know how to recreate some things. For example, conditions on the Earth for when our central star, the Sun, goes out. If we manage to become a Class B civilization, we'll learn to adjust conditions to be independent of the Sun. That means we might be able to learn how to live even without it. And if we level up and become Class A, we'll know how to recreate cosmic conditions and produce our own cosmos in our laboratories. We think of the world we live in through 3 dimensions of space: east, west, north, south, and up, down. There's also 1 dimension of time, which means we can distinguish past from future. A 5th dimension would represent 1 more extra dimension of space. The theory of its existence was first mentioned in the 1920s. It was inspired by the theory of gravity by Albert Einstein, who said space-time is warped by matter and energy. We can't perceive these 4 dimensions, but we see how an object moves and attribute it to gravity. And maybe there's some other force, like the electromagnetic force, that's more than 1,000 times stronger than gravity, that could explain things going on in that extra dimension of space. The 5th dimension is curved in a way we can't see it, but the idea about it was mentioned in a string theory. It considers the universe as really small strings of mass energy, not as particles. They vibrate in 10-dimensional space-time, considering 6 dimensions are rolled up way smaller than a single atom. That led to the picture of the universe as a 3D island that floats in 10-dimensional space-time. Also, the 5th dimension might be an excellent explanation to tell us more about dark matter. That's the invisible stuff with a mass, but we can't see it, nor can it interact with ordinary matter. And dark matter is 85% of all the matter in our universe. The universe can't be still. It's constantly in motion, either contracting or expanding. We used to think there were 100 billion galaxies, but it turns out there are more than 1 trillion. The galaxies are moving away from each other. This is what it means when scientists say the universe is expanding all the time. There are voids between galaxies that sometimes stretch millions and millions of light years across. They can seem empty, but they can also contain way more matter than we can find in galaxies. Still, stars usually can't be formed there because the matter between those areas has lower density. But there's still plenty of so-called intergalactic stars. A good example is the Virgo galaxy cluster, 10% of which are intergalactic stars. We don't know how exactly they got there, but there are 2 possible ways. 1. Stars can collide, merge, or pass close to another galaxy, which can kick it off from its parent galaxy. Option number 2. A supermassive black hole can accelerate a star to very high velocities if they have a close encounter, which can, again, make a star be expelled from its parent galaxy. If you could have a giant magnet, you could even pull something out from the vicinity of a black hole. That's possible if the magnetic field near a supermassive black hole is as strong as the black hole's gravitational field. But it doesn't work if we're talking about material that's already beyond the black hole's event horizon. That's a spot with a gravitational force so powerful, not even light can get away. You'd need to accelerate this material to the speed of light, at least, to get away. For that, you'd need an infinite amount of energy. But a magnet could help if something's heading toward the black hole but didn't get inside yet. When someone mentions a black hole, you might get a picture of some giant void in space. But the Milky Way is most likely full of thousands of smaller black holes that float around the galaxy. When a star comes to its end, it will destroy itself in a supernova explosion, which is a cataclysm of energy. In that explosion, the densities in the core will reach an intense enough state that nothing will be able to escape. At the same time, the major part of the star explodes outward, but a part of it collapses inward, creating a black hole. The bigger the star, the bigger the hole. The black hole then swallows everything that comes in its way, including other stars as well. When a star gets sucked up into the black hole, it's ripped apart because of the strong gravity inside the black hole. Some of its parts fall into the black hole, while others get ejected at incredibly high speeds. Some black holes might have been formed in a different way. The early stages of our universe were, to say the least, pretty chaotic. It had high temperatures and pressures, and was in a state that shaped the entire cosmos. Under the right conditions, any old gas patch may have shrunk itself to become a black hole. And they came in many different sizes, from something that weighs a couple of pounds to giant masses like thousands of suns, and those in between. They aren't really black. Black holes are areas with strong gravity, and no object can escape when it gets inside. They feed off electromagnetic radiation, such as light and space particles. Since they're consuming matter all the time, black holes give off a dark glow. The Earth is not that close to the inhospitable edge of the solar system. We're the 6th planet from it. Scientists made a pretty cool 3D map of our solar system, where we can see what the edge looks like. It took them 13 years to design it. The boundary is called the outer heliosphere. It marks the area in space where the solar wind, which is the stream of charged particles our sun emits, gets deflected and draped back by the radiation coming from the empty region beyond our solar system. The inner layer of the heliosphere is where the sun and the planets have a rough shape of a sphere, while the outer layer is not that symmetrical. This asymmetry happens because our sun is moving through the galaxy and goes through friction with the radiation in front of it.